2k different solutions. Basically, the one which has the least coming weight, that's the distribution for maximum likelihood decoding rule for a binary symmetric channel. So let's take we have a 7-4 code whose paradigmatic matrix is given like this, and
Hello, can you hear me? Okay. Uh, I am Sachin, a PhD student in the EC department at the Indian Institute of Science, and I'll be conducting problem solving sessions every Saturday until the course ends at from 6 to 8. So I am not the regular TA for this course. So if you have any doubts about the logistics of the course, exam dates, assignment questions, some mistake in the evaluation, such type of stuff you'll have to ask in the discussion forum in the website. So I am not associated with any of that. We'll only be conducting problem solving sessions and clear your doubts if possible. So the way I will conduct this session is, first I'll show you the question. It is on the screen, hopefully you can see it, and I'll give you a few minutes, maybe 2 3 minutes to solve it. You can put your answers in the chat box if you are confident, and then I'll go ahead and tell you the answer. If there is some explanation needed for any of the questions, I'll tell it. If it's just a theoretical question, then I'll give you the right answer and we'll move on. Alright, let's start with the first question. Which of the following is the correct order in a digital communication system? So it's a multiple choice question. There will be four options. It's the same thing for your weekly assignments. I hope you have seen them. There will be multiple choices and you have to select one. Sometimes there may be a mistake and two answers might be correct. In that situation, you can contact the regular TAs, and they usually tend to give marks if you have selected only one option in that situation. Alright, I'll give you 2 minutes to think about this. Maybe you can go back to your notes. This digital communication system model is given as a diagram in the lecture, so you can go back and check that. So this is the basic communication system model. There is an information source. For example, now I am speaking to you, that is a source of information. And in this case, there will be a transducer before the source encoder, which will convert my voice variations to electrical signals. That's your microphone, and that electrical signal will be converted by your source encoder into a more easy to handle form. That is, it will quantize it and convert it into bits, and then before it gets transmitted to you through this Google Meet, it will be encrypted so that someone outside of this meeting cannot get the information here. And then there will be an encoding that goes on to reduce noise. That's the channel encoder. And once that is done, you can't send electrical signals directly. It's not efficient. So you will do modulation, and then you will send the modulated uh, electrical signals through your Wi-Fi or whatever network you are using, and then it goes through the channel. Here mostly, if it's between two towers, it will be wireless signals. If it's through an optical cable, if you're using broadband, it will be through an optical cable. And then the reverse process will happen at the receiver side. So it will be demodulated, then decoded, then decrypted. And again, if you want to say you are listening to it through a speaker, so it will be again converted to voice signal. So that is a basic communication system which is used everywhere, not just in coding. So out of these, you have to see which option is right. So first option says you do digital modulation first and then source encoding. So obviously that is wrong. Second option says you do encryption and then source encoding. That's also wrong. Third option says digital modulation and then channel encoding and then through the channel. So that's also wrong. So you do channel encoding first and then modulate and send it to the channel. So right before the channel, right before sending it to the channel, you'll do modulation, and right after receiving from the channel, you'll do demodulation. Similarly, right from the information source, you'll first do source encoding, and when it's sent back to the sink, you'll do source decoding. So, as many people have pointed out, it is option 4. I'll put that as D. Whenever you are free. Okay, we'll go to question number 2. Is it visible or should I blow it up? Okay, consider an information sequence being coded using R is equal to 1 by 3 repetition code. So for every message bit, there are 3 coded bits, such that a received sequence S is equal to 110 010 111 001 is obtained. Find out the decoded sequence if the decoding is done based on majority decision rule. Again, I'll give you 2 minutes. Try to solve it. Okay, this is a repetition code, and what you do in a repetition code is if you have message bits u0, u1, u2, then the code word will be, it's 1:3 repetition code, so u0 will be repeated thrice, u1 will be repeated 3 times, and u2 will be repeated 3 times. This will be transmitted, maybe there will be some error, and you will receive some other code word. So uh, if you receive something like 110, then it has two ones and a single zero, so it has more ones than zeros. So you will decode this as 1, even though you might have actually sent 000 and two of the bits got flipped and you got 110. While decoding, you don't know. So it is more likely that 000, that 111 goes to 110 than 000 going to 110. So that's why we use the majority decision rule. Now if we consider the given received sequence 110, 010, 111, 001, and group it into 3-bit groups. So 110 has majority 1, it will be 1. 010 has two zeros, so we'll decode it as 0. 111 has three ones, so we'll decode it as 1. 001 has two zeros, so we'll decode it as 0. And that turns out to be option A. Alright. Here we saw 1:3 repetition code, but there's no reason it has to be only 1:3. You can have 1:r repetition code, or you call it R repetition code. Where each bit is repeated R times. And if you make it an odd number of bits, again you can use the majority decision. If R is odd, you can use the majority decision rule there also. The difference between what is the difference between this 3 repetition code and some higher 5 repetition code? Difference is that rate will change. So rate is 1 by 3 here for a 3 repetition code. For a 5 repetition code, it will be 1 by 5. So you're actually sending more bits. So you need more bandwidth. But what is the benefit then? The benefit is that error will be smaller. You can go back and calculate the probability of error in both these codes, for the 3 repetition code and for the 5 repetition code, for 7 repetition code. You can assume a binary symmetric channel with some probability p. Arbitrarily you can choose, say 0.1, and find out what is the probability that you'll get an error. And you will find out that if you use more number of bits, the error will decrease. At the same time, the number of bits you need to send has to increase. So it's a compromise. Depends on how many bits you can actually send and how much error, what is the accuracy you want, what is the least possible error that is permissible. So in most cases we would like to our bandwidth is a lot more important. Well, it also depends on the application, but we'll try to keep it at the maximum possible error level that we can, so that we send the least number of bits and we add the least number of redundancy. So let's say this, you have this 3 repetition code and you have message with 10,000 bits message. Let's say you're using a BSC with 0.001 probability of error, something like that. And then if you use a 3 repetition code, you need to send 30,000 bits now. So if it's just 1 bit, then you need to send 3 bits, it might seem okay. But if you are sending 10,000 bits, then the additional number of bits you are sending is 20,000. So that's a lot. And with this, you might be able to get p error around 0.99 something. You'll have to do the calculation yourself. You'll get something like that. Okay. But Claude Shannon had a result which said that if the rate of your code is less than the channel capacity, then for sufficiently large messages, you can get arbitrarily, you can get your probability of error to be arbitrarily close to 1. So that is, if you do some math, I am not going to do the math here. If you use Claude Shannon's logic, you can show that just this same probability of error, you should be able to get it with about 10,150 bits. So can you see the difference? You are getting the same error, but here you need to send 30,000 bits. Shannon says you can do it with only 10,150 bits. So you are only giving 150 additional bits. Here you are using 20,000 additional bits. So that's the whole. Uh, that's the main part of error control coding. That is finding codes with as little extra bits as possible that give you as good of an error value you want. So from this perspective, this repetition code is not that good. You need so many bits for the same probability of error. Okay, so that's the goal of error control coding. Alright, we'll move to the next question. Given a parity check matrix of a linear block code, they've given there are 4 rows and 7 columns. This corresponds to a what type of code? 6-2 linear block code, 6-3 linear block code, 6-4. I'll give you 2 minutes to solve it. Also be careful, this is a parity check matrix and not a generator matrix. You have to be careful about that. Okay, so here you know that if you have a code word V, then VH transpose must be 0. So the dimensions of the code word, if it's n 1 is to n code word, if there are n bits in the code word, then there must be this H transpose must be n by something. So the H transpose must have n rows. That means it should have H should have n columns. So the number of bits in the code word n is the number of columns in H. So n is equal to 6. There are 6 columns in H. Then you would think that you might say there are 4 rows. So n minus k is 4. So k is 2 and it's a 6-2 block code. But that's not true. What you have to do is you have to find the rank of the parity check matrix and rank in the binary field. Okay, so finding the rank you will learn in linear algebra. You should have learned it by now. The same procedure even in binary field, except that you don't need to subtract anything here. 1 plus 1 is 0 in binary. 0 plus 0 is also 0. 1 plus 0 and 0 plus 1 are 1. So you add the first row to the fourth row. So you'll get 1 0 0 0 1 1 0 1 and 0 1 0 0 1 1. So we eliminated this one. Next we have to get rid of this one. So we'll add the second row to the fourth row. You will get 1 0 0 1 1 0 0 1 0 0 1 1 0 0 1 1 0 1, and you can see that second and fourth row are the same. So when you add those rows you will get 0 0 0 0 0. So you have a row of zeros. That means the fourth row is dependent on the other 3 rows. So n minus k here will be equal to the rank of h, and since we are using binary numbers it will be rank in the binary field, and the rank here is 3. So k is actually minus 3, which is 3. So like Sandeep Kumar initially thought, Hello. Can you not hear me? Okay. So when you are trying to find the number of message bits, you will have to first find the rank of your parity check matrix. Okay. And that rank will be equal to n minus k, where n is the number of coded bits and k is the number of message bits. So n minus k will be the number of parity bits that are used to generate parity bits. And that will depend on number of independent rows. So if one row is dependent, the parity check generated by that row will not be useful to us. It will be redundant. So this, what I mean by that is, if you have this, you need a h into v transpose or vh transpose to be equal to 0, right? So if you have a code word v1 to v6 and then you multiply with h, so this is actually v transpose, right? Now it should be a 0 column vector, right? And from that you will get four different conditions, right? v1 plus uh, v4 plus v5 must be 0. Second row of h will give you v2 plus v5 plus v6 is equal to 0. Third row of h will give you v3 plus v4 plus v6 is equal to 0. Final row of h will give you v1 plus v2 plus v4 plus v6 equals 0. So it will appear as if there are four independent equations that you have, right? But the thing here is, suppose you add these two equations, what will you get? v5 plus v5 in binary, it will simply be 0 if you add the same bit. So you will get v1 plus v2 plus v4 plus v6 equals 0, which is nothing but the fourth equation. So in actuality you only have three equations for the code word, existence of the code word. So the fourth condition is redundant. So that's the reason why the rank is more important than simply the number of rows in H, because one of the rows is just a redundant row that doesn't give you any more information. Okay, we'll move on to the next question. And in the end, if someone didn't understand this, I'll come back and try to explain it in a better way. Okay, question 4. Which of the following is an example of a linear block code? Try to solve it. Try to remember the conditions for a for code words or a set of code words to be considered a block code. So there are properties for block codes, right? First property would be zero code word must be in the block code. And why is this the case? This is because if you have, so a code word is nothing but some message symbol multiplied by the generator matrix, and each message symbol or each message word must have a corresponding code word. So suppose let G be any generator matrix. G is of size k by n, this is of size 1 by k, this is of size 1 by n. So you take the 0 message word and multiply it with any generator matrix. You will end up with a vector of zeros. So this 0 must be a code word, and this is true for any generator matrix. So that's why every set of code words in a block code must contain the 0 code word. You can see option 1 and 2 both don't have the 0 code word. So both these are not correct. They can't be linear block codes. We are only left with two options. For that we can use another property. Sum of two code words must be a code word. Of course, remember that this is true only for linear block codes. There might be other codes in which you don't have the 0 code word, and there might be other codes in which sum of two code words may not be a code word. This is only happening because every linear block code can be expressed as the product of the message with the generator matrix, and it will follow the properties of linear algebra. So why is this the case? Let's say you have one code word C1 which is equal to U1 into generator matrix G, where U1 is some message word. C2 is another code word which is equal to U2 into G, where U2 is another message. Now the sum C1 plus C2 will be U1G plus U2G, which will be nothing but U1 plus U2 into G. And you know that, of course, this comes from linear algebra. If U1 and U2 both belong to some field, then their sum is also belongs to the same field. So U1 plus U2 will also be a possible message vector. That is, if you are considering 3-bit numbers as messages, say you have 101 is one message, 110 is another message, their sum will be 110, which is another 3-bit message, 3-bit number, right? So that's also a possible message that you can have. So U1 plus U2 is some U dash, which is also a message, and any message into the generator matrix will give you some particular code word. Let's call it C dash. That means the sum of C1 and C2 is equal to some other code word C dash. So that's another property of linear block codes. The sum or difference of any two code words must be a code word. And you can check now in option C. You have 1111 that belongs to this code block 1111, and you have 0001 which belongs to the same code book. So 0001 also belongs to C. 1111 plus 0001, which is nothing but 1110, does not belong to C. 1110 is not here. So this cannot be a linear block code. If you check the properties for the fourth option, you will find out that both properties are satisfied. So C is actually a possible linear block code. No, not C, option D. Okay, that's how you find out if a set of code words is a could be a linear block code or not. Let's go to question 5. What should be the rank of the parity check matrix for 7-4 linear block code? This you can use the fact that I had told you in the previous problem. Rank of parity check matrix of a linear block code is equal to n minus k, where n is the number of bits in the code word and k is the number of bits in the message. So you have a 7-4 linear block code. Hello. Hello. So there's a lot of external noise. That's why I was using earphones. Unfortunately, the earphones are not working properly. So by next time, I'll try to get new earphones. For now, you'll just have to bear with the noise. Now I am audible, right? Okay. So we finished question 5. Let's go to question 6. For a systematic 8-4 code, the generator matrix is given as G is equal to whatever they are shown on the screen. What is the minimum distance of this code? I'll give you some more time for this question. It will take a bit of time. I'll go to the washroom and come back, and you can try to solve it within that time. All right. Sandeep is saying it's 4. How did you get the 4? So in this type of question, first you have to find the parity check matrix. See, yes, from 0, yeah, that is true. You can generate all the possible code words and then check the distance from 0, 0, 0, 0. But how do you know that some code word doesn't have only 2 or 3 bits in it, 2 or 3 ones in it? You can't generate. There are 4 rows here, right? So the basis has 4 rows, 4 different basis vectors are there. So if you try to generate all possible code words, then you will have to find out 16 different code words. And then from that you will find the uh, minimum distance from 0, 0, 0, 0. So the code word with the least Hamming weight, the Hamming weight of that will be the minimum distance then. But for that you have to generate all the code words, right? For this problem, it's okay if there are 8 rows. Then what will you do? You'll need 2 power 8. Yeah, so for small problems that will be fine. For larger problems, the way you can do it is, first you see that G is in standard form. So it's in the form PI, where the first 4 columns form P, last 4 columns are in the form of identity matrix. From that you can easily find H, the parity check matrix, which is I P transpose. Let's write that down. I and then P transpose from here. So now you have the parity check matrix. From this you find out what is the minimum number of columns which add to 0, or what is the minimum number of dependent columns. Sorry, yeah, minimum number of columns that add to 0. So just with one column you can't get 0. No 2 columns also give you 0. You can check with 3 columns, even that won't give you 0. Then you check with 4, and you can see that uh, there are different combinations, but if you add the last 3 rows, you will get 1 0 0 0, which is exactly the 4th row. So the first row plus the last 3 rows will you sorry, I meant column. not row. First column plus last three columns will give you a column of zeros, and that will be the minimum distance of your code word. So d minimum is equal to minimum number of columns of H matrix that add to 0. And why is that the case? Suppose we write down the code word in column vector form like I did in one of the previous questions. Then H into V must be HV transpose must be 0, right? Let's say you have two different code words. H V1 transpose is 0 and H V2 transpose is 0. That would mean that H V1 minus V2 transpose is also 0, right? But V1 minus V2 must be another code word. Okay. Now we have H V1 minus V2 transpose is 0. What exactly are you doing here? You have H is a matrix which will have a certain number of columns. It will have n columns. Then V1 minus V2 transpose is some vector which has n elements in it. When you multiply a matrix with a column, you are essentially taking a linear combinations of the columns of H. If you have seen in this is explained very nicely in Gilbert's Rank's linear algebra course. In the textbook also you can find it. So one way to think of matrix multiplication is that if you had V1, V2 to Vn here, then this product is, and these are all columns, not single elements. These are single elements. So this will be nothing but V1 H1 plus V2 H2 plus etc. plus Vn Hn. Okay. So it's a linear combination of columns of H. Now what does that mean for this particular problem? You have V1 minus V2 transpose, H times V1 minus V2 transpose is 0. Now suppose the minimum distance is only 1, right? That means there are two code words which differ only in one place. That's what you mean by minimum distance. Take those two code words and subtract them. What will happen? If you have some code word 1 0 0 0 0, the other code word is 0 0 0 0. These two differ only in one place. If you subtract the second one from the first one, you will simply get the first one. Now you multiply that with H. What will you get? You will get H times 1 0 0 0, which is nothing but the first column. You are saying that is 0, which is not true. Columns of H are not 0. Now suppose you say that the minimum distance is 2. That means there must be two code words which differ only in two places. Say you have these two code words. They differ in two places. You subtract them. V1 minus V2. That will also have to be a code word. So If you subtract that, you will get 11000. This must be a code word. Multiply h with this code word. What will you get? h1 plus h2 must be a 0 vector, right? So you have found that the minimum number of columns that you need to add to get a 0 vector is only 2 columns. Similarly, if the minimum distance was 3, there must be two vectors that differ only in two code words that differ only in 3 places. When you multiply with h, you will get a sum of 3 columns, and that will have to give you a 0 column. So that is the reason why in the parity check matrix, the minimum number of columns that add to 0 will give you the minimum distance between vectors in the code book. Did you understand the logic? Maybe I'll leave that here. As a side note. And even if you didn't understand all that, at least remember this fact. Minimum distance is equal to minimum number of columns in H that add to 0. Okay. Let's go to question 7. 7 is actually very simple. An illustration has been done in class in the main lecture notes. I don't know about the problem solving session done by Professor Adrish. There was one problem solving session, right? I haven't looked into that, but in class itself one example was given. So U is a message block with 4 message bits: U0, U1, U2, U3. That's the message sequence. And V is the code sequence: V0, V1 to V7, 8 bits. The relation between U and V is given. For each of the code bits, they've given how you should generate that code bit. So V0 is U0 plus U1 plus U2. V1 is U1 plus U2 plus U3, and so on. They just want you to find the generator matrix. And like we saw in class, okay, there's one thing that I need to tell you. Here in this course, we are writing these vectors as row vectors. The code word V0, V1, V2, V3, V4, V5, V6. So you need not write them as row vectors. You can take column vectors also, but you have to be careful. In many of the formulas that you write with G, H and all, when you say V is equal to UG, we are assuming that this V is a 1 by n vector, U is a 1 by k vector, and G is a k by n matrix. So the dimensions will be proper. You could simply write this as an n by 1 vector, an n by k matrix with a k by 1 vector. So in this way, this will be a column vector, right? There's one column and k rows. It will be U0, U1 up to UK. This will also be a column vector. This will be an n by k generator matrix. And you might end up with the same message and the same code words except in column form. The generated matrix will obviously be different in this case. It will be the transpose.
So there's nothing wrong with writing your code words and message words in column vector form, but you can't mix them up. You can't write the code word in column vector form and your message word in row vector form. Then you'll end up in trouble. So when you write VH transpose is 0, you are assuming V is a row vector. You could have simply written HV is 0, where V is a column vector. But in this scenario, if you have taken V as a row vector, then you will have to, if you transpose both these things, you will end up with HV transpose is 0. So these are different things, even though they are saying the same thing. So here our V is a row vector, so we have to transpose it and then multiply with a parity check matrix. But if you started out with a column vector, then you could simply write HV. So that's not a big problem, but just be careful, that's all. Okay, now we can move on to writing the code words in terms of, okay, there are 4 bits in the message, so there will be 4 rows in the generator matrix. So this will be 4 by, and there are 8 bits in each code word, so the number of columns will be 8. It's a 4 by 8 generator matrix. Now V0 is U0 plus U1 plus U2, so it's 1 1 1 0. Simple matrix multiplication. U0 times 1 plus U1 times 1 plus U2 times 1 plus U3 times 0, which will be nothing but U0 plus U1 plus U2. Simple linear algebra, nothing else. That's why these block codes are very nice. It's just linear algebra. So if you study linear algebra, it will be very easy to understand everything in block codes. Now V1 is U1 plus U2 plus U3. V2 is U0 plus U2 plus U3. V3 is U0 plus U1 plus U3. The remaining things are simply V4 is U0, V5 is U1, V6 is U2, V7 is U3. So yeah, whatever you have written down in the chat box is correct. So that's all this question is asking. They had given options, but I didn't bother copying that down. Anyway, there's only one way to solve this. You get the
Excuse me, sir.
ah.
Could you please repeat the question, sir? We can't understand this sum, sir.
This problem, what you have to write the generator matrix. We had studied in class, right? The code word will be
Yes, sir.
the message symbol multiplied by the generator matrix. So you have to
Yes,
find
sir.
out what this G is.
Okay, sir.
And for that they have given these rules. How do you get V0? You get V0 by adding U0, U1 and U2. Okay. V1 is U1 plus U2 plus U3. V2 is U0 plus U2 plus U3. V3 is U0 plus U1 plus U3. V4 is U0, V5 is U1, V6 is U2 and V7 is U3. They have given the relation between message bits and the code bits. Now you have to find out what is the generator matrix from which you can directly multiply and get your code word. And you can see, you know, matrix multiplication, right?
Yes, sir.
This is row vector multiplied by a matrix. When you multiply the row with the first column, what will you get? You'll get u0 into 1, which is u0, plus u1 into 1, which is u1, plus u2 into 1, which is u2, plus u3 into 0, which is nothing but 0. So the first element of this multiplication is u0 plus u1 plus v2, which is equal to v0. Two vectors are equivalent if corresponding elements are equal, right? So if v0, v1, v2 is equal to 1, 2, 3, that means v0 is equal to 1, v1 is equal to 2, and v2 is equal to 3. So similarly, this v0 will be equal to the first element of the vector you get by multiplying this. The first element you get is multiplication of the row with the first column. So this is equal to u0 plus u1 plus u2. The second element you get is u0, u1, u2, u3 multiplied with second column. So it is u0 into 0 plus u1 into 1 plus u2 into 3 plus u3 into 1. Similarly, you can do this. So that will match with whatever rules that I have given. So from these rules, I have written down this matrix, okay? We'll go to question 8. Which of the following is a valid parity check matrix corresponding to the code described in question number 7? So they're using the same generator matrix that was given in the previous question. From that, we have to find the parity check matrix. This is very simple, right? This is in the systematic form. You can see this is in the form of pi. So this 10000100 00100001 is in the form of identity matrix I4, and the remaining part will be your P. So to find H is nothing but IP transpose. So you first write down I, of course you have to be careful here. This is a k by k matrix. Here it's an n minus k by n minus k by n minus k matrix. So it's ik. In H it will be I n minus k. This case n minus k is equal to k. So you will write I and then P transpose. P transpose is nothing but 1110 0 111 1011 1101. So that is the parity check matrix for the given generator matrix. And that will turn out to be option C. Any doubt in this question? It is straightforward. You write G in the systematic form and then you simply find H directly by writing the transpose of the matrices. Of course, you can only do this if your G is in systematic form. There is no guarantee that your G will be in systematic form. In that case, you can't directly write like this. You'll have to make changes, corresponding changes in H also. It won't be that much more difficult. So there's no guarantee that this G will always be in systematic form. You have to remember that. So in that case, you will have to use the fact that GH transpose is equal to 0 and try to find H from that. Okay, question number 9. Given a linear block code with H matrix given by the diagram shown there, the matrix shown there, what is the syndrome corresponding to the received vector is 1 0 0 1 1 1. So the syndrome is nothing but R multiplied by transpose of H. R is 1 0 0 1 1 1. H is also given. H transposes 1 0 0 0 1 0 0 0 1 1 0 1 1 1 0 0 1 1. Now it is simply matrix multiplication. You can do it the normal way, or so when you are multiplying a row by a matrix, it is nothing but the linear combination of the rows of the matrix weighted by the values in the row vector. So it is nothing but 1 times the first row plus 0 times the second row plus 0 times the third row plus 1 times the fourth row, 1 times the fifth row, and 1 times the sixth row. So this will be nothing but 1 times the first row is 1 0 0 plus you have zeros, 2 zeros next, so second and third row are ignored. Then you have 3 ones, so it's 1 0 1 plus 1 1 0 plus 0 1 1. So 1 0 0 plus 1 0 1 is nothing but 0 0 1. 1 1 0 plus 0 1 1 is nothing but 1 0 1. And the sum of these two is nothing but 1 0 0. So the syndrome is 1 0 0. So the option B. So if your received vector is R, it will be nothing but the code word V plus error vector E, when you multiply it with H transpose, we'll get VH transpose plus EH transpose, and by the property of the parity check matrix, VH transpose is 0. So this will be equal to EH transpose. So that is the syndrome. That will tell you what class of errors has occurred. From that you can identify what class of error has occurred, and then in the end the code word will be nothing but, since it's binary, it will be R minus E, but in binary it will be nothing but R plus E. So you know the received word. If you can find out what the error vector is most likely to be from this syndrome, you can get your code word back by adding the error to it. I think this should have been explained in class also, how to do decoding using the syndrome. Okay, one last question. Which of the following statements is false regarding the standard array? There are 2 power k elements in a coset. All elements of a coset have the same syndrome. To minimize the probability of error in BSE, the most probable error pattern is chosen as the coset leader. There are 2 power k coset leaders. So which one is false? You'll have to go back to the last lecture video and check it out yourself, where they have explained how syndrome decoding is done. So there are 2 power n minus k coset leaders. So that statement is false and the rest of the statements are true. There are 2 power k elements in a coset. All elements of a coset have the same syndrome. To minimize the probability of error in a BSE channel, binary symmetric channel, most probable error pattern is chosen as the coset leader. That's all for today's problem solving session. Is there anything you want to ask? There are no questions regarding convolutional codes this time. Those will probably be covered when we come to this topic in detail in later lectures. So if you are if you have forgotten your linear algebra, it's better to go and brush up because it will be used a lot in this course. So binary symmetric channel, first you will have to give me what is the probability of error in the binary symmetric channel itself. What is the crossover probability? You are not given that. Where is figure 1? So you have a source. You have a source that is giving out 1 with probability 0.2, 0 with probability 0.8, and then this 1 will go to 0 with probability 0.1, right? And it will stay at 1 with probability 0.9. Similarly, 0 will stay at 0 with probability 0.9 and go to 1 with probability 0.1. Correct? Hey, you can't ask me assignment questions. I'll get in trouble now. Well, you think I won't tell you the answer directly, but I'll at least give you a direction. See, what you are asking is what is the probability that you will get 1-0, right? How can you get 1-0? Multiple ways in which you can get 1-0. Suppose the source first of all emitted 1-0 and there was no error, right? The BSC did not cause any errors at all. Then you will get 1-0. Or suppose your source emitted 1-1 and there was an error only in the second bit, then also you will get 1-0. Suppose you source sent 0-1 and both bits got flipped, there are error in both the bits, then you will get 1-0. Suppose 0-0 was transmitted and only this first bit was flipped, there was error in only first bit, and also you get 1-0. So in all 4 possible transmissions from the source, you could end up with a 1-0. But the probability for each of these cases will be different, right? From 1-0 to get 1-0, no error must occur, right? From 1-1 to 1-0, second bit there must be an error. That is, only in one bit there must be an error. From 0-1 to 1-0, both the bits must be flipped. So 2 errors must occur. 0-0 to 1-0, again only one bit is flipped. So each of these will have a certain probability of happening. First of all, there will be a probability of the source emitting 1-0. Right, first it has to emit 1, then it has to emit 0. There will be some probability for that. You have to calculate using these 2 values. Then from this to go to this, from 1-0 to stay in 1-0, there will be some probability, right? That depends on this channel. So you find that out. And then you multiply those probabilities. You will get the probability for this first scenario. You do the same for the next one. What is the probability that source emits 1 1? You find that out using these two probabilities. Then once source is emitted 1 1, what is the probability that the channel will cause it to turn to 1 0 from 1 1? That you have to find from these probabilities. Then multiply, you will get the probability of source emitting 1 1 and then the channel changing it to 1 0. So you will get some probability for this case. Do the same for this case and this case. So you will get 4 different probabilities. Add all the 4 because any of these 4 can't occur at the same time. Only one of them can occur. So add all 4 probabilities. You will get the probability that 1 0 is transmitted. 1 0 is received. Okay. That's the method. Computation you have to do. If I do that, then I'll get your marks. Alright, any other questions? Okay, that's it. If there are no questions, I'll just... So usually this is supposed to be a 2-hour session. But in most cases, since there are only 10 questions, it won't go up to 2 hours. Maybe next class I'll start with a recap. I'll write down some notes and start for 15-20 minutes. I'll give you a revision of what was done in class and then start with problem solving. Otherwise, about 1.5 hours, we'll stop. I'll just stay here for 10 more minutes and then leave. You guys can leave now.